Good morning. Mostly all are available, I think. So today we are going to complete these computations. Okay. So once again, considering these methods, so we are going to have the turn-off methods to be of natural commutation, in which natural commutation. So in which circuits these natural commutations are going to be employed? In which circuits natural commutation is going to be employed? So natural commutation is going to be employed in AC circuits, as AC the current value is going to be reaching to zero maximum and again falling to zero at the desired instant. The conducting devices are going to be turned off automatically. So natural commutation is going to be employed in the AC circuits. But coming to the DC circuits, whenever the power supply is going to be DC, in that case you are going to have a finite you are going to have a finite magnitude of voltage and current provided across the device. So what will happen once the device comes to the conduction by a gate pulse? Then there will not be any favorable condition. There will not be any favorable conditions for the device to be turned off. So what we need to do means we need to force the current flowing through those particular devices to fall less than the holding current. So that particular circuits or that particular method of turn off is considered to be as a forced commutation. Why it is going to be called as a forced commutation means, by naturally power circuit, the current, if the current falls less than the holding current value, then it is considered to be as a natural commutation. Okay. So in the DC circuits, what will happen means, the current and voltage magnitudes are going to be finite, so its value will never fall less than the holding current value. Its value will never fall less than the holding current value. So what will happen? We need to force the current through the turn on device to less than the holding current value. For that, we are going to use certain elements, most probably the inductors and capacitors. In some methods, it may be an auxiliary devices, auxiliary thyristors, auxiliary diodes, like that. Okay. So forced commutation is going to be, so for in the case of forced commutation, DC circuits are going to be considered as a power source, and as the current and voltage magnitudes are going to be always of a finite magnitude, so the device which is turned on may not be turned off, or may not be turned off by the power circuit. So in that case, we need to reduce the current to less than holding current. That is, the current flowing through the device is forced to reduce to holding current value, less than the holding current value. Okay. So as the current falls less than the holding current, the device is going to be turned off. For this, we are in general around 6 to 7 methods are going to be considered. 6 to 7 methods are going to be considered, and these 6 to 7 methods are going to be on the basis of the placement, on the basis of the connecting of the commutating elements in the circuit. Okay. So that some may be connected in series with the load, some may be connected in parallel with the load, some may be connected in parallel with the switching device, some may be connected with an auxiliary device, like that. On that basis, those are going to be classified to be as class A, class B, class C, class D, and class E commutations. Okay. So these commutations are going to be always, they are going to be employed in the DC circuits. Okay. So in the last session, we have seen about class A, class B, and class C commutation, isn't it? So whenever you are going to consider these commutation circuits, the main power circuit is going to be the same, provided with a DC voltage. To this, additionally, the commutating elements are going to be connected. In all these, the commutating elements are going to be connected. Okay. So whenever we are going to consider whenever you are going to consider this, we are going to uh, consider these by the commutation circuits and the waveforms. Okay. So here, whenever you are going to consider, is the screen visible to you for commutation circuits? Anyone respond? Is the screen visible to you?
Yes, sir.
Yes, sir.
Okay, so here, whenever you are going to consider these the basic elements used in the computation are going to be nothing but the inductors and the capacitors. Okay, so as the main purpose of the inductor is going to limit the capacitor charging rate of the capacitor. Okay, so by what is the purpose of these two means, one thing is the capacitor, as it is going to be a energy storage element, it is going to hold a potential. Okay, this particular potential across the capacitor, may be either providing a reverse current through the switch device, ultimately reducing the net current flowing through the device. Okay, or else applying a reverse voltage across the switch device, Okay, so the purpose of this inductor is nothing but in order to limit the charging rate in the capacitor, the inductor is going to be used. So if a small inductor is going to be considered, then you are going to have a fast quick charging of the capacitor. Okay, if a large inductor is going to be considered, then you are going to have a slow rate of charging of the capacitor. So that means whenever we need to make the device to be turned off, then if the capacitor voltage are going to be reversing quickly, then ultimately you may have a tone off, tone on, tone off, tone on, like that. That bandwidth between the turn on instant and again blocking the voltage is going to be completely dependent on the oscillations of this LC circuit. Okay, so here basically coming to these commutation circuits, either majorly there are going to be three types, that is going to be depending upon the elements employed. So one is going to be by means of LC elements. Second one is going to be by means of uh, by nothing but called as the current commutation, and the third one is considered to be as the voltage commutation. Okay, so voltage commutation means applying a reverse voltage across the conducting device. Current commutation means applying a reverse current through the conducting device. So current commutation, voltage commutation, and in general resonant commutation. So a resonant commutation is going to be nothing but simply by this RLC circuit. Okay, as you know that whenever you are going to consider these commutation circuits, the basic circuits are going to be based on the resonance. That is going to be the condition of resonance formed by this load and these commutating elements. Okay, so in the last session we considered related to this class A commutation. Once again I am briefing this class A commutation. In this class A commutation, what is the normal power circuit? Is the normal power circuit is going to be considered simply by eliminating these L and C. Okay, inductor and capacitor. So that is the simple circuit in the DC is going to be provided with a DC voltage, switching device, and the resistor RL. Okay, so what will happen whenever a gate triggering is applied to this device? As it is going to provide continuous current, the device is going to be continuously in the conduction, isn't it? So then how to turn off this device? Then to turn off this device, what we need to do means we need to force the current, this current, to less than the holding current, less than the holding current. So to reduce the current value to less than the holding current, what we need to do means we need to place the commutating elements in the circuits. So those commutating elements in the circuits are going to be this inductor and capacitor. This inductor and capacitor. Okay, so whenever the inductor and capacitor are going to be placed, here the condition for commutation is going to be happened when these three elements are going to form an underdamped circuit. That means the load resistance value is going to be fixed, isn't it? The load resistance value is going to be fixed. We are going to choose depending upon the application. It may be 300 ohms, it may be 600 ohms, or it may be some other value. Okay, then with this particular resistance value, we need to choose the capacitance value and inductance value such that the condition for the underdamped should be satisfied. In that case only, the connection of this inductor and capacitor is going to turn off this device. Is it clear? Okay. So here, in the case of this class A commutation, whatever the commutating elements that are going to be placed, those elements should be matched with this resistance which is connected earlier, such that it forms an underdamped condition. Underdamped, it is providing an underdamped oscillations. Okay. So in that case, what will happen, as the RLC circuit is going to be considered, which is familiar to you in the previous classes. Okay, so you are going to have, if a constant DC voltage, DC current is going to be provided, due to this underdamped condition, you are going to have the current which is going to be drastically increasing, reaching to maximum, and again it is falling to zero. Again its value is going to be reversed, and again its value is going to be reaching from zero to maximum, maximum to zero, like that. So that is why this method of commutation is going to be completely considered as of underdamped resonant circuit. Okay, so you may consider the waveforms provided here to be like this. Before this particular instant, the device is in under blocking state, so there is no current. Okay, so whenever you are going to consider this instant, so here what we are going to consider, on one axis you are going to consider the gate current, on one you are going to consider the capacitor voltage. This is going to be the voltage across current across the SCR, that is nothing but the load current, and the voltage across the SCR. So here, whenever you are going to consider these waveforms, so the gate signal, as you know that the gate signal is going to be provided with a minimum time, instant. Why it is going to be chosen to be of minimum means, it is chosen to be of minimum as to reduce the gate circuit losses. You may continue this gate signal to be up to this instant, but the gate signal required by the device is going to be short, and it should be in this particular manner. If it is chosen to be of continuous signal, then there is no use of providing the gate signal all the time, in spite of uh, having a much gate power losses. Okay, so once the device is going to be provided with a triggering pulse, what will happen, you are going to have a current which is flowing through the device circuit. As the current flowing through the device, what will happen here, you are going to have a capacitor voltage which is going to be charging. So this waveform represents here the capacitor voltage is going to be recharging, and the capacitor voltage charges and reaches to its maximum value. As we know that whenever the capacitor voltage reaches to its maximum, simply it acts to be as an open circuit, so the current value becomes zero. So you are going to have the current which is going to be reaching from zero to maximum to zero. The current value falls to zero. As the current value falls to zero, what you are going to get, the device is going to be turned off. So that means here you are going to consider a reverse voltage provided, isn't it? This particular reverse voltage provided here is going to be due to the turn off process. As in the turn off characteristics, we considered a reverse voltage across the device, isn't it? So from this particular instant to this particular instant, it is going to be the turn off process, and you may consider the time to be as the sum of turn off time plus the circuit turn off time. After that only the device is capable of blocking the voltage. So this, from this particular instant to this particular instant, the device is ready and it moved to the blocking state. So the forward voltage is going to be blocked. Here from this point to this point, you are going to have a zero voltage, isn't it? So that means the conducting instant is from this point to this point. Conducting instant is going to be from this point to this point. It is as we are neglecting the on-state voltage drop, simply representing the zero waveform. If we are going to consider the on-state voltage drop, a magnitude of 0.5 volts is represented here. Okay, so that is for a class A commutation. you may have different current waveforms provided on the connection of the capacitor. So the waveforms here are going to be for the series capacitor, connected series, in series, and in shunt. Okay, so then moving to the other, that is going to be the class B commutation, isn't it? So in the case of this class B commutation, it is considered to be as the resonant pulse commutation. It is going to be considered to be as a resonant pulse commutation. Why it is going to be called as a resonant pulse commutation means a current pulse, from the resonant elements, a current pulse from the resonant elements, that is going to be nothing but the capacitor discharge current, is going to be provided in reverse to the switched device. Okay, a pulse from the capacitor is going to be provided to the device. So to the conducting device, this resonating pulse is going to make the conducting device turn off. So it is considered to be as a resonant pulse commutation. Okay, so in this resonant pulse commutation, there are going to be three modes of operation. There are going to be three modes of operation. Okay, so first one is the thyristor is going to be in the off state. The thyristor is going to be in the off state. Whenever the thyristor is going to be in the off state, simply if the power supply is going to be turned on, then immediately you are going to have the current conduction provided from this positive to this inductor, inductor to this capacitor, capacitor to this load, and negative. So the capacitor is going to be charged here with a polarities of upper plate positive and lower plate negative, isn't it? Okay, so this is mode 1, in which the capacitor is acquiring a charge of plus positive charge on the upper plate and negative charge on the lower plate. Okay, after that what will happen, we are going to, in the mode 2, what we are going to do means, we are going to give the triggering pulse for this device. Whenever the triggering pulse is going to be provided, then what will happen, this device comes to the conduction. When the device comes to the conduction, you are going to have two currents flowing through the device circuits. Okay, one is going to be the load current, which is represented by this red color dotted arrow. So from supply positive to this switching device to this inductor, inductor to this supply negative. This current is going to be the main load current, which is going to be flowing. Okay, after that what will happen, initially when this device is going to be in the off state, the charge is going to be acquired in the capacitor, isn't it? As the capacitor is going to be charged completely, it has the tendency for discharge. That means it will always tries for a closed path. As soon as the closed path is going to be provided, by the conduction of this device SCR, the capacitor starts discharging. Okay, what is the capacitor discharge path? It is going to be from this positive plate to this inductor, inductor to this main switching device, anode, cathode, and negative. Okay, so this dotted representation represents the current which is going to be the discharge path of the capacitor. As the discharge cycle completes, the current moves from this positive plate to this particular plate. So the charge acquired by the capacitor is going to be this positive and this negative, isn't it? The charge acquired by the capacitor is going to be lower plate positive and upper plate negative, isn't it? Okay, so what will happen, as it is going to be again completely charged, what will happen, it again have the tendency for discharge. The capacitor searches for the conduction path. Whenever you are going to consider the capacitor path, path, the capacitor path is going to be, still the device is going to be in the conduction, still the main device is going to be in the conduction. So what will happen, it starts discharging and simply injects a current. The capacitor current is going to be injected onto the device. So whenever the capacitor current is going to be injected onto the device, so what will happen, whenever the capacitor current is equal to the load current value, then the resultant current flowing through the device, will become less than the holding current, so the device is going to be turned off. Okay, so here whenever you are going to consider this in the next mode of operation, the capacitor discharge path is going to be from the lower plate positive to the switching device to the inductor to this negative plate. So as this is going to be happen, this is considered to be as a resonant pulse of current injected onto the device in the reverse direction. So the total or net current in the device is going to be reduced, and it comes to the blocking state. Okay, so whenever you are going to consider these uh, blocking, whenever you are going to consider these waveforms here, you are going to give the triggering pulse for the SCR. This represents the gate pulse provided, and this represents the load current which is going to be flowing. So whenever the device comes to the conduction, you are going to have a load current. So the load current is going to be flowing at this particular instant. After that, what will happen? The capacitor is going to be charged. Capacitor is going to be in mode 2. The capacitor is going to be discharging in the reverse direction, in the same direction of the load current. So you are going to have a spike in the current. The spike here in the load current is nothing but the sum of the load current and the capacitor discharge current. Sum of load current and the capacitor discharge current. After that, what will happen? Again, the capacitor starts discharging the current in the reverse direction. So what will happen? The net current across this is going to be, the resultant current across this is going to be the resultant of load current and the capacitor current. So its value decreases and falls to 0. Okay, as this falls to 0 here, as it falls to 0 here, the device is going to be turned off. The device is going to be turned off, and after that, it is capable of blocking the forward voltage, making the device to be in the forward blocking mode. And again, later a device is going to be provided to the triggering by by the gate pulse at this particular instant. So is it clear with this? Okay, this is similar to that of the voltage waveform provided. Voltage waveform, when the device comes to the conduction, 0 voltage will be prevailing across the device. When the device is going to be in the turn off process, a reverse voltage is going to be applied. When when the turn off process is completed, it blocks the forward voltage. So from this point to this point, it is going to be in the blocking state, blocking the forward voltage. Again, it comes to the conduction. Okay, so the capacitor, the current across the SCR will be like this. Okay, the current across the SCR will be like this point to this point, the device is off, so 0 current, and this point to this point, the device is going to be in the on state, so you are going to have a current which is going to be nothing but the load current. Okay, so this is class B commutation or resonant pulse commutation. Why it is considered to be as a resonant pulse commutation means a capacitor current is going to be considered to be as a pulse, and it is injected in reverse to the main conducting device. Okay, so then moving to the third one, that is going to be the class C commutation or complementary commutation. Class C commutation or complementary commutation. So in the case of this class C commutation or complementary commutation, what it is going to be done means, uh, uh, in uh, in order to turn off the main device, an auxiliary device is going to be considered. So in these complementary commutation circuits, always there will be two devices. Always there will be two devices. One device is going to be the main device associated with the load current, and the other device is going to be the auxiliary device, which is intended or which is placed in the circuit to turn off the main device. Okay, so here whenever you are going to consider this, the circuit will be like this. The generalized commutation circuit will be like this. Okay, so the normal power circuit will be with a power supply, resistive load, switching device. This forms the normal power circuit. Okay, whatever that is connected in parallel with this resistor and switching device, this is going to be the complementary circuit. Okay, so whenever you are going to consider these complementary circuit, the complementary circuit consists of a load resistance R2, capacitor, and a complementary device or an auxiliary device. Okay, how it is going to be happened here means, whenever initially the two devices are going to be in the off state, main device, auxiliary device are going to be in the off state, isn't it? When the two devices are going to be in the off state, then what will happen? This uh, uh, this is going to be an open circuit. This is going to be an open circuit. Is there will be any current conduction path? Is there will be any current conduction path? So there is no current conduction path provided from this positive to the negative. So there will not be any current flowing in the circuit. Okay. So what will happen after that? What we are going to do means, we are simply going to make the triggering for this main device. So you are going to give the triggering pulse for the main device. Whenever the triggering is provided for the main device, then you are going to have two currents flowing. That means the current is going to be flowing in two paths. The first path is going to be from supply positive to this load resistance RL to the switching device and return. This is going to be the load current IL. Okay. In addition to this current, what you are going to have here, you are going to have another circuit providing the conduction path. So what will happen? The capacitor, the current is going to be splitting, and some part of the current is going to be moving through this resistor, capacitor, and this switching device, and it is going to be returning. Okay. So this current is going to be nothing but considered to be as the capacitor current, capacitor charging current. So as the current is going to be moving here, you are going to have the charge is going to be acquired in the capacitor to be as positive on the right side plate and negative on the left side plate. Is it clear? Positive on the right side plate and negative on the left side plate. Okay. So here what to then what how to turn off the main device means, as they are going to be, as both are going to be connected in parallel, as both are going to be connected in parallel. So what it is going to be done means, this device is going to be intended completely to make this device turn off. Okay. So what will happen? The capacitor is going to be charged with a potential of positive and negative. So okay, what will happen? The capacitor is always having the tendency to discharge. Okay. So but the discharge path is going to be from this positive, this switching device, to this device, negative to the negative terminal, isn't it? So until the capacitor is going to be, until the thyristor is going to be provided with a triggering pulse, the capacitor is going to be holding the charge. At the desired instant, somewhere here, you are going to give the gate pulse for the auxiliary device. Once the gate pulse is whenever the gate pulse is going to be provided with a triggering pulse, what will happen? This comes to the conduction. When this comes to the conduction, this positive terminal is applied across the cathode, and negative potential of the capacitor is connected across the anode. So you are going to have a reverse voltage provided across the device. So what will happen? Due to this capacitor current, the net current in the device is going to be reduced to less than holding current value. So the device is going to be turned off. So the device is going to be turned off. Okay. So what will happen? You are going to have the device to be turned off. Okay. So the device is going to be turned off, and you are going to have the turn off process. You are going to have the turn off process, which is going to be by turning off the capacitor, turning off the auxiliary device, isn't it? So one second, please. Okay. So a little bit problem with the mouse pointer. Okay. So here, whenever we need to turn off the device, we are going to give the triggering pulse for this. Once the triggering pulse is going to be provided, then this device is going to be turned off. So you can observe that in the waveforms. So the load current is going to be provided to the load by the main switching device. Whenever you are going to give the triggering pulse for the auxiliary device, the device is going to be turned off. So the current value falls to 0. And from this particular instant to this particular instant, the device is going to be in the blocking state. Again, the main device comes to this, main device comes to the conduction. Main device comes to the conduction at a gate instant provided here. Then you may get a doubt here, how this device is going to be turned off, isn't it? So whenever you are going to consider this device, the device is going to be turned off as the other device is going to be, as both are going to be provided in parallel. When this device comes to the conduction, the voltage provided across this device is going to be nothing but the capacitor voltage, isn't it? Again, if this device comes to the conduction, then the on-state voltage drop, of this device only appears across this until the capacitor is going to be charged. So the device is going to be in the blocking mode. So when this device comes to the conduction, it is going to be turned off. When this device comes to the conduction, this is going to be turned off. So it is considered to be as a complementary commutation. It is going to be considered to be as a complementary commutation. Okay. Then moving to the other, you can refer all the modes of operation in the PDF provided. Okay. So then moving to the fourth one, that is going to be the class D commutation or impulse commutation. So this is going to be called as a parallel capacitor commutation, Here in this, what it is going to be happen means the capacitor is going to be connected in parallel. Okay, the same thing is going to be the operation is going to be the same. But the thing is, the capacitor, the commutating element is going to be connected in parallel with the main device. Okay, so the main device is going to be T1, auxiliary device is going to be T2. This inductor is to limit the charging rate. Diode is going to block whenever the capacitor is charged in reverse direction. Okay, and this is going to be the circuit here. Okay, so whenever we are going to consider the normal operation in mode 1, T1 is going to be turned on. When T1 is going to be turned on, simply the current conduction path is from positive to this T1 load and return, isn't it? Okay, so then this capacitor is to be charged. How the capacitor is going to be charged means there is no path provided for the capacitor to be charged when both the devices are going to be in the off state, isn't it? So what will happen means we are assuming that the capacitor is going to be a pre-charged capacitor, with polarities of positive and negative. Okay, so before the operation starts in the circuit, you are going to place a charged capacitor in the circuit. Okay, after that, what will happen? This T1 is going to be provided with a triggering pulse. You are going to have a current conduction provided from this point to like this. Okay, after that, what will happen? As the capacitor is going to be charged, it has a tendency for discharge, and the discharge path is going to be from this positive to this T1 to this negative. So ultimately, when the charging cycle completes, the lower plate is going to be acquired with the positive polarity and upper plate is going to be acquired with negative polarity, isn't it? That conduction path is going to be from positive to this T1 to this inductor to this diode to this negative plate. Okay, whenever it is completely discharging, the polarities are going to be reversed. You are going to have a positive plate in the lower and negative plate in the upper. Okay, so this is going to be happened. Okay, after that, what you are going to do at the desired instant, whenever we need to make the main device turn off, we are going to give the triggering pulse. For this auxiliary device. Okay, whenever the triggering pulse is provided for this auxiliary device, then positive potential, it acts as a short circuit. Positive potential of capacitor is applied across the cathode, and negative potential is applied across the anode, isn't it? So a reverse voltage is going to be applied across the switching device, conducting device. So the device is going to be turned off. So this is also called as a voltage commutation, impulse commutation or voltage commutation. So what is the purpose of this diode here? What is the purpose of the diode here? Means if this diode is not placed here, if this diode is not placed here in the uh, discharging of in the charging of capacitor in reverse polarity, so that means what will happen? Initially positive, negative. When this device is going to be turned on, what will happen? It acquires a positive polarity and it acquires a negative polarity, isn't it? Positive polarity and negative polarity. So what will happen? It is positive. If this diode is not placed, simply an inductor is placed, the capacitor has a discharge path provided from the load to this. Then there is no commutation provided to the main device. To provide the commutation or reverse voltage to the device, this particular potential should be blocked, and that is going to be done by this diode, which is considered to be as a blocking diode. This diode is considered to be as a blocking diode. Okay, so you may have the waveforms same as of the previous. So this is going to be the current, main current. This is going to be the load current. This is going to be the current through the switching device, and main device is going to be turned on here, and auxiliary device is going T2 is going to be turned on here. So from this point to this point, the main device is going to be turned off. Again, it is going to be turned on here. Okay, so this represents you may have the capacitor voltages and you may have the capacitor currents. Those are going to be represented here like this. Okay, so this is related to the class D commutation, and coming to the other, that is going to be the class E commutation. Okay, so in this case of this class E commutation, what it is going to be done means it is considered to be an external pulse commutation. External pulse commutation. So what is this external pulse commutation means? In order to make the device turn off, what we are going to do means we need to either we need to reduce the current less than the holding current value, or else we need to apply a reverse voltage across the device, isn't it? So the reverse voltage is going to be applied here. A reverse voltage pulse is going to be applied to the cathode, between the cathode circuit and the supply. Okay, so here that is happened by means of a pulse transformer. So a pulse is going to be a 1:1 pulse transformer is going to be considered, and it is going to be connected from between anode and the load circuit, and here you can observe a reverse pulse, reverse voltage. So this reverse voltage is going to be applied. This reverse voltage is going to be applied by the pulse transformer. Okay, once the reverse pulse is going to be applied, this cathode becomes more positive than this anode. So the device is going to be turned off. So the device is going to be turned off. Okay, so this is related to the external pulse commutation or class E commutation. So in general, this is going to be considered in very small less applications. The previous are going to be mostly considered, and this is going to be considered in very less applications. Okay, then coming to the other, that is the last one, that is going to be the class F commutation or AC line commutation. So this comes under the AC line commutation. This will never comes under the forced commutation. It comes under the AC line commutation, which we considered in the previous, that is going to be the natural commutation method. The circuit here is going to be same as in the natural commutation, provided with the AC voltage, and you are going to have the AC supply voltage waveform represented, triggering of the device, and automatic turn off of the device as the current falls less than holding current. So this is going to be the conduction for the device. This is going to be the off state for the device. Again, this is going to be the conduction. Okay, so this is class F commutation or AC line commutation. So whenever you are going to consider from class A to class E, all the commutations are going to be considered. All the commutations are going to be considered in the DC circuits, and class F commutation is going to be considered in the AC circuits. All these are going to be the turn off methods. All these are going to be the turn off methods employed for the SERs for making the conducting device to be turned off. Okay, so is there anything? So we may consider the remaining topics in the next session. Okay, so then is there anything doubt related to these computation circuits? Once refer to these computation circuits provided to you, and if you have any doubt, you may simply approach me. Okay, so please respond anyone. Is there is any doubts for you?